So this is an intro level talk, so if you already know all of this, you might be a bit bored. I'm going to tell you how the internet works. If you go to computer science at a university, typically this is like a full semester, so half a year of typically around 70 hours of courses, and the total duration of time you spend on this is given as 180 hours. So I'm not going to be able to go in total depth of how everything works. But that being said, I have a couple of goals, and why I don't expect you to remember everything that I'm going to talk about today. I hope that I'm going to be able to convey some of the core concepts and abstractions that are used in computer networks in general and in the internet specifically. And I also want to take away some of the fears of computer networks. I feel like some people are like afraid to approach computer networks, thinking that they are quite complicated. And I think that if you understand some of the building blocks, they're actually quite simple to figure out. And when you understand the building blocks, it's kind of easy to understand how some things might work and what's happening on your network. And I also want to give you some pointers on how to experiment with computer networks if you're interested in this after this, and how to debug common problems that you might encounter in your networks at home. So, typically when you interact with the internet nowadays, you're probably going to do it through a browser, either on your computer or on your phone. And my talk mostly is about what happens when you enter an internet address like www.emfcam.org and hit enter. So the first thing that I want to mention is what gets transferred over the network. So if you go to your browser and hit view source, you see something like this, which is the HTML source code of the website, which says how it looks like, what text is on the website, what images are going to be downloaded and embedded. And that's what your browser gets from your internet to show you the website. In principle, how this works is fairly simple in some ways. So how you can imagine this is that you have small postcards. So this starts with me writing a small postcard that is like, from me to emfcam.org, website please. And then emfcam.org answers and gives me the website. And this really is a little bit like postcards in that the amount of information that you can send at one go to your network and get from your network is rather limited. So on a postcard you have limited space, and like to get a full web page back you need to split up the information across several different cards because you cannot fit it on one. And this also is the case on the internet. On the internet the typical message size that you can send is about 1,500 bytes, or 1,500 characters. If you are sending a message that's more than 1,500 bytes, it has to be split up across several of those postcards. In networks, you typically call them packets. And no matter what you do on a computer network, your information will always be split up, and that's one of the important core concepts. Like, even if you have something that looks like you have a connection that just flows, like you are talking to someone over a phone, over the internet, or you're having a video conference of the internet, it still means that all of the data that you are sending and receiving is split up into little blocks of 1,500 characters that you send and receive to the internet. And it's not just not just the internet that works like that. Like, even if you connect a monitor via DisplayPort, it also uses like these kind of small packets that it sends around it. For the rest of my talk, I'm mostly going to talk about home networks. So if you use your internet at home, you typically connect to something like this that you have standing around somewhere. So you have this device connects to your internet provider at the one side, and you either plug in a network cable or probably use Wi-Fi nowadays to connect to the internet through it. And to explain how this works, let's start at a little bit of an abstraction, and imagine that you are in a school class. And the school class is not quite set up like normal. Instead, everyone is sitting quite spread wide out apart. You can't see each other, and you communicate via postcards that you send via pneumatic tubes to each other. And each student gets one pneumatic tube, and all of the students' pneumatic tubes arrive at the teacher. And the first time that the class comes together, the teacher and the student arrive in random places. The teacher gets all of the pneumatic tubes. The teacher has no idea what student is behind which pneumatic tube, because everyone showed up for the first time. So assume that we have two students in the class. One is called Alice and the other one is called Blair. And Alice knows that Blair is in their class and wants to send a message to Blair. And the teacher will gladly forward this. So what Alice does, Alice just has one pneumatic tube. Alice can just say, I have a message to Blair, and send it out. When the teacher gets that message, the teacher sees, oh, this is a message from Alice. So the teacher can go and label the pneumatic tube that they received the message from as Alice is behind this tube. And then the message is for Blair. The teacher doesn't know where Blair is. So what do they do? They go and are like, okay, if I just copy the message and send it to everyone else, Blair will get it because they are somewhere. So the teacher copies the message, sends it to everyone, and then if Blair wants to reply, they can send a message back to Alice, and since the teacher knows where Alice is sitting, they can send the message directly back to Alice without having to send it to everyone or to try to figure out where Alice is, because they already have the label on the tube. And after they get the message from Blair, they can also label the tube for Blair. And this is how a lot of your home network works. So if you have a switch on your home network, so like a device where you plug in like several computers, this is exactly how a switch on your home network forwards messages between the connected computers or other devices. It just learns where everything is on the first message that it receives. How does this work on a slightly different class? So let's say that we have a class where there are more students, and there are so many students that the teacher doesn't want to deal with all of the pneumatic tubes. Instead, there is like a hierarchy where some students have several pneumatic tubes and then send their information on to the teacher. And let's say that everyone has come together for the first time, no one knows where anyone is, and Alice wants to send a message to Taylor this time. And it kind of works in the same way. Alice sends out the message, and then since no one knows where Taylor is, everyone just sends them to all of the other connected pneumatic tubes, being like, at some point of time, this will hit Taylor, and while they are doing that, everyone writes down that the message came from Alice and puts that on the pneumatic tube that they got the message from Alice from. So how do computers do that? Because networks do this, because networks don't use names. So the network that you are most likely to have at home is either Ethernet or a Wi-Fi network. So Ethernet for cabled network and Wi-Fi obviously for Wi-Fi. And both of these are substandards of the same standard group, which is IEEE 802. It doesn't really matter what it stands for. What's important is from a functional perspective for us, wired and wireless networks work exactly the same. And in these kind of networks, devices that are part of the networks are identified by an address that looks like this. This address can either be called a MAC address, a hardware address, an Ethernet address, a device address, depending on who you ask. It doesn't really matter. What's interesting about it is that each computer and even each network card that you have in your computer has one of these addresses, and the address is programmed or burned in on the time that your computer is produced. So each network interface on every computer in the world that does Wi-Fi or connects to an internet has a globally unique address, which is really important because, assume that you have a class where you have two Alices. Humans are really good at figuring out, well, one of them is Alice A and one of them is Alice B. Humans are really good. Computers are not good at dealing with non-unique names. So it's really important that names are globally unique, and if you show up to a new network, no one else will ever have the same name as you. If you go to your network settings on your computer and click on this, you typically can find the MAC address or Ethernet address somewhere. So this is Mac OS on the left side, where it's called a MAC address, and the Linux command line interface, where it's called an Ethernet address on the right side. And at this point of time, I want to talk a little bit about a piece of software that is called Wireshark. So let's say that you are interested in networks and want to see how this happens at your home network. Wireshark is a piece of software that you can install no matter what operating system you have. It works on Linux, Mac OS, Windows. And when you start it up, it looks something like this. This might look a little bit overwhelming, but it's rather easy. It shows you the network interfaces that you have on your computer. And the squiggly line that you see at the right shows activity. And the squiggly line is really helpful because it shows you which network interface is the one that actually stuff happens on. And so you can just select a network interface that has the most activity, which will typically be the one that you're connected to with the internet. And if you click on that, you start seeing a screen like this, where every line on the screen is a packet that is transferred from or to your network. And when we click on one of the lines and expand down here, you can see what I just told you about. So here inside this yellow circle, you see there is a destination address and a source address, and both of these are those Ethernet addresses that I talked about. So they are in essence the names of the computer, and the message is sent between those two addresses. So after hearing this, you might, or you should probably ask yourself, so how does this scale? Because if at a home network, it's quite clear how this works, but assume you want to talk to emfcamp.org or to Google. You cannot just send out a message randomly and hope that everyone sends it on till it hits a computer of EMFcamp, and that everyone remembers how to send it back to you. And the way that this works is that we introduce a small layer of abstraction on top. So assume that instead of just being a class, we have a whole school. In a class, students might just show up randomly and sit at random places, and you have to figure out where they are. But if you're building a school, you probably know exactly which classrooms you have, where the classrooms are, how the classrooms are connected, where the corridors are, and where the pneumatic tubes or the cables are that connect the different classrooms. So if you have someone that wants to send a message from class 1 to class 5, as you put a lot of energy into building up your school and building up the connections, you know what the optimal path is, and that a message should probably travel directly like this from class 1 to class 5 without hitting anyone else in between. So how do you do that on the internet? You use the final tool that you use for these are IP addresses. You probably have seen those before. Nowadays, there are two different versions of IP addresses. IP stands for Internet Protocol. There's the Internet Protocol version 4, which is the top, and the Internet Protocol version 6, which is the bottom, and both of them are used simultaneously. At home, you are still somewhat more likely to encounter version 4 addresses. In principle, they work very similarly. IPv6 addresses just look more intimidating because they are longer, because you're more likely to encounter before. I'm mostly going to talk about version 4 addresses, which look like this. And if you break them up in components, they are quite easy. In essence, there are two parts to it. The front, 3 numbers, all numbers go from 0 to 255, identify the network, and the last number identifies the host, so the computer or device on your network, typically. So if you go back to our school example, how this looks like is we have all of our classes, and now we give each one of our classes a different network, because each class has a bunch of students. So for example, class 1 gets all addresses that start with 192.168.1. Class 2 gets all addresses that start with 192.168.2. Class 5 gets all addresses that start with 192.168.5. And then you give everyone who is in any of the classes one of the IP addresses in that. So a student in class 1 could, for example, have IP address 192.168.1.3. And now if someone from class 1 wants to send a message to class 5, you can use the IP addresses to figure out where the message is supposed to go, because once it hits your teacher knows, oh, this is destined to class 5, based on the IP address. Then it can go to the school coordinator who knows, oh, this goes to class 5. He can send it on to the teacher at class 5, who then can try to figure out which student it has to go to. So to talk about how this looks like on the network cable in your network, let's make this a tiny bit easier and say that you just have a small class, 3 students, a teacher, and the teacher is directly connected to the internet. And now say someone from the internet wants to send a message to Blair in this case. And what happens is that the message arrives from the internet, from your internet provider in this case, and arrives at the teacher at Casey, because Casey is the only person that is connected to the internet. And Casey gets the message and sees that it's an internet protocol message and it's meant for Blair, and sends it on. And how this looks like on your network is, if you break this up in steps. So you still have your network message, and we learned earlier that on network messages are in essence addressed between individual people. So in this case, on your local, in your classroom, the message still comes from your teacher. So the teacher sends a message to Blair, and this is the Ethernet layer. And so your network layer. And inside of that message is the internet protocol message, which says, this is a message that comes from the internet, from this IP address, and the destination is this IP address, which belongs to Blair. And inside of that IP address, you have the actual content that you are transferring, which in this case is hi there. This is the payload of the internet protocol message. Typically, it's more than just a short message. Typically, you have something like, if you access a web page, you access it via HTTP or HTTPS. If you access it via HTTP, you have HTTP is the hypertext transfer protocol, which is the protocol that you're using to transfer web pages. In there, if you use HTTPS, you have TLS, which is an encryption protocol, which then contains HTTP, and then you get your web page. And one of the really important things that I want to take away from this is that what you do in networking a lot is that you just layer levels of abstraction on top of each other. So we have the local network here, which contains the internet protocol message, which contains the actual information that you are interested in receiving. If we go back to Wireshark, we can also see this here. So this is the same packet that we had earlier. We have our Ethernet message with the source and destination on the local network. And just below that, we have the internet protocol message that says that this is from this source IP address to this destination IP address. So this packaging is exactly what happens in your local network at home. And I talked a little bit about that you use switches for your local network. Switches only do not do internet protocol stuff at all. They just forward messages in the local network. There's another device that is called routers at your internet provider. They might look something like that, and they are the devices that are responsible for figuring out which direction an internet protocol packet has to go to reach its destination. At home, you typically have something like this. So what kind of device is this? If you turn it around, the labeling of the ports gives it away a little bit. You might not be able to read it. In this case, the yellow ports say LAN on them, which means local area network, and the blue ports is WAN, which means wide area network. And in essence, behind the yellow ports is something like a switch that just forwards stuff in your local network, and between the yellow ports and the blue ports is a router. So this is kind of a device that's a little bit of both. So, but how do we talk to the internet? So let's say that you are someone, either you're a person that shows up to class for the first time, and your teacher is connected to the internet. Your teacher needs an internet protocol message, an IP address to be able to talk to the internet. They get this from their internet provider in a way that I'm not going to mention, because there are several ways that this works, but they have an IP address. So if you show up to the network, you have a name, because that's burned in. So you're Alice, and the first thing that you do is you ask, what is my IP address? And then the Casey replies, your IP address is 192.168.0.2. So that moment you have an IP address. This also shows why you need a name too, because if you didn't have a name, you couldn't ask for an IP address, because you can't just you need something so that information can be sent back to you, some kind of identifier. So you need the two levels. You need the lower level, the Ethernet level, to be able to ask for an IP address in the first step. And this is exactly how IP addresses are typically assigned to you in your local network. So if you go back to the Linux command line and type IPA, you see your IP address in the IP lane. In Mac OS, under network settings, you also see your IP address, and this is exactly how your computer figures out what the address is on the local network. This is also exactly how it works at EMF. Once your computer joins the EMF Wi-Fi, it just sends a message out, what's my IP address, and it gets an answer from another computer at EMF that will tell it, this is your unique address, go, continue. So, but I was talking about this scenario. So when we go to www.emfcamp.org, we put in an address, we do not put in an IP address. So how does this work? And the answer is that there is an additional system that is called DNS, which is the domain name system, which maps domain names, like emfcamp.org is a domain name, to IP addresses. And how does this work? So, if you go back to the example that we just had, we have Casey, who is connected to the internet via its internet provider. And when Casey connects to the internet, they either manually have to type in the address of a DNS server on the internet during configuration, or your ISP automatically tells you the name of your internet address, of the DNS server. When Alice connects to the network and gets the IP address via DHCP, Casey also tells them, hey, if you want to know the domain name of a server, just send the message with the request of what the domain name, what the IP address for a domain name is to me. So if Alice wants to know the domain name for emfcamp.org, they send a message to Casey that is like, what is the domain name of emfcamp.org? Casey is like, okay, I know the address of a DNS server on the internet, and sends the question onto the DNS server on the internet. The DNS server on the internet either randomly already knows what the address of emfcamp.org is and can just reply, it's this IP address, or if they do not know, they do this in a similar way. There is a hard-coded list of IP addresses of like top-level responsible servers on the internet that you can ask who is responsible for all addresses in ORG, and then you go to that and ask, okay, who do I ask for addresses in ORG? And then you go to send a message to the ORG name servers and are like, who is emfcamp.org? And EMF, they tell you, this IP address is responsible for emfcamp.org, and then you ask those who is www.emfcamp.org, and they will send you a reply. But that happens in the background. You do not see that in the local network. You just send out a question and you get a direct reply back, which first goes to Casey, and then Casey sends it on to you. And if you go back to Wireshark, this is exactly how it looks like. So in the green bar on the top, you can just put protocol names to filter your network traffic by so that you don't see everything because there's a lot going on. I typed in DNS there for the domain name system, and then I clicked on the line where the request for emfcamp.org is, and you can see that here, which says queries emfcamp.org A, which is a query for an IP address, doesn't really matter why. And then a couple of packets down when you click, you see an answer to this, which is emfcamp.org is at IP address 37.27.241.111. One really interesting thing about this is when your internet doesn't work, when you type in a name, you can try figuring out if the fault is DNS, which it often is, or if it's somewhere else. And one of the ways that you can do that is that you can send a message to something without using the domain name, but just using the IP address. There's a tool that's called ping that's available on Windows, Linux, everywhere that you can use in the command line. And if you type ping IP address, it will just send a short message to an IP address. And if the IP address replies, you will get a pong back, and it will tell you that you got 64 bytes back. And if you know an IP address on the internet that is likely to always be up, 9999 is one of those. You can just hit ping 9999 if your internet doesn't work, but if this works, then DNS is broken and you can change your DNS server, for example, or you can complain to whoever is running your DNS server. If this doesn't work, then something else is lower level is down and you do not have any internet protocol connectivity to your provider and probably your link is down. So, but how do packets on the internet go to the right place? I just talked about the example of this big school where you just build things up and you know which direction you have to send things. But the internet is obviously not like this. Because the internet is like lots and lots of networks connected together and you have to know which direction to send stuff. So this looks something like this. So each of the clouds here is a network on the internet. The top left one is EMF camp, and the other ones are just other networks on the internet. And to be able to participate like on the internet as a network that sends messages directly to the internet, which your internet provider typically does, you need a unique identifier that identifies your network on the internet. And each network that participates on the internet is known as an AS, which stands for Autonomous System, and has a unique number that you can request from a registration agency. And EMF camp is AS 60,079, for example. And EMF camp has a whole bunch of IP addresses. They have all IP addresses starting with 92.118.29, and most of the IP addresses starting with 151.217. And EMF camp wants that people can reach it. So what it does is just EMF camp knows the next internet networks that it's connected to directly, that it has wires to, and it just sends out a message that is like, hi, I am AS 60,079. These are the two networks that belong to me. If you encounter any messages, any IP messages that are bound to these addresses, send them on to me. And then the next network takes this message and is like, hi, and sends it on to everyone that is connected to them. And it's like, hi, I am AS 65,542. If you want to reach these messages, send them through me and I will forward them. And you do that kind of till you hit a loop, at which point you stop so that you don't forward this for all eternity. But you forward this till it hits, in essence, every single router of every provider that is part of the internet. And this protocol that does it is called BGP, the Border Gateway Protocol. You might have heard of it. So if someone from the bottom left wants to send a message to EMF camp, now they have two choices. They either can go right and send a message through AS 64,500, AS 65,542, or AS and then to EMF camp at AS 60,079. Or they can send it the other way, directly to 65,542 and then to 6079. And obviously, what you do is you choose the shorter version that goes through the least amount of networks. And this is actually, in principle, how routing on the internet works. You just send out the information, which IP addresses you have, to all connected providers on our connected networks, and then you choose the shortest path out of the knowledge that you have. If you're curious which networks a message of you goes through, there are programs like this one is called mytraceroute on Linux that you are just like, how do messages go from me to emfcamp.org? And you can see on the left a list of ASs, so autonomous systems, that your message goes through. And if you're interested, you can look up who that message goes through. If you want to play with things like this more, there's cool things like network simulators. There are two big ones that I'm going to mention. There are more, are GNS3 and Container Lab. GNS3 is more based on graphics, where you can just click together a network and experiment with really expensive hardware that is just launched inside of your computer, and click yourself switches and routers together and do stuff like that. And if you want to play with BGP, you can, for example, there are networks where people play with BGP, where you use VPNs to connect yourself together, and then you can set up on your Raspberry Pi, if you have one at home, you can set up a BGP network and be like, I have this address room that you get allocated, and talk to other people and see how you configure that, see all of the messages that I exchanged, play around with having several, or how you do it so that if one link fails, that it automatically fails over, and all kinds of stuff. And so, in essence, If you're interested in any of this, I just want to encourage you to play with computer networks. It's not that complicated, it's a lot of fun. If you want to see what's going on your network, there's software for that. You can just install and then directly do that. If you want to run some services for fun, use Linux, install some network services. You can run DNS servers, DHCP servers, web servers at home and just figure out how they look like and then look at the network traffic. You can play with expensive hardware by just using simulators. You can become part of like virtual networks where you can practice how it works like to be an ISP. And if you have any questions about this, I will be at the Q&A tent just outside there on the right for the next 15 minutes or so.